Greetings, Brian here, and today we're going to talk about free fall. And free fall is the motion that things undergo if the only force acting on them is the force of gravity, which we will call the weight force. It's directed downward. If the only force at work is gravity, things are in free fall, and the motion of everything in free fall is the same. Now, this topic is covered in Chapter 2 in the book. If you haven't read Chapter 2, and specifically if you haven't read the section on free fall, I want you to pause right here, go back, read the textbook, because what I'm going to talk about assumes that you have seen this. And you've seen that the acceleration of free fall is negative 9.8 meters per second squared. So if I drop an object and it starts out with an initial vertical velocity, so that's Vy of 0 meters per second, so it's at rest. After 1 second, it's moving downward at 9.8 meters per second, so the velocity is negative 9.8 meters per second. After 2 seconds, it's moving downward at 19.6 meters per second, so the velocity is negative 19.6 meters per second. After 3 seconds, it's moving downward at 29.4 meters per second, so the velocity is negative 29.4 meters per second. The change per second is 9.8 meters per second per second. That is the acceleration. It is also the slope of the velocity versus time graph, 9.8 meters per second, and the slope is constant because the acceleration is constant. But we talked about dropping something from rest, not something that's clearly falling, but you have free fall if something is going up as well as if it's coming down, because in both cases the acceleration is negative. So here I have a picture of an object in free fall, and it's dropped from rest, and it kind of like the velocity vectors get bigger and bigger and bigger, more and more negative as it falls. That is free fall. But it's also free fall if I was to throw it up. So if I imagine starting by not dropping something from rest but throwing it upward, the velocity vectors would look like this. They are positive and getting smaller. That is a negative change. Then when it reaches the top, it's at rest, turns around, comes back down, and then it's negative and getting more negative. And that is also a negative change. Both of those have an acceleration of negative 9.8 meters per second squared. Both of them are free fall, going up or coming back down. And that's an important thing to keep in mind. We call it free fall, but free fall just means this. The only thing that's acting is gravity. That is the only force that is at work. It doesn't mean something's falling. You're in free fall. The acceleration is negative 9.8 meters per second squared. And that's true if an object is moving upward or if it's coming back down. Now I want to test your understanding of free fall, and I want to do that by asking a couple of questions. First off, imagine this. An arrow is launched vertically upward, okay? It moves straight up to a maximum height, then falls to the ground. The trajectory of the arrow is shown right here. Here's the question. Which of the following graphs, A, B, C, D, or E, best represents a graph of the vertical velocity of the arrow as a function of time? And we're told you can ignore air resistance. Go ahead and give that some thought. Pick which graph looks the best. I'm going to go ahead and pause the video, think about it. I'll be back. Well, we're told you can ignore air resistance. So what that means is the arrow is in free fall. And if you're in free fall, the acceleration is negative 9.8 meters per second squared. And so that means the slope of velocity versus time graph is going to be constant. And so we're looking for a graph with a constant slope. And there's only one version here, and that's graph D. The velocity is continually changing. And so we're going to get the velocity starting out positive, going to 0, and then going negative. The change is always negative. It's going more positive and becoming smaller, negative, and the magnitude is increasing. Both of those negative changes. That's the right graph. Now here's another test case. We have 5 arrows with the noted masses, and they're shot upward at the noted speeds. We're going to assume as well that you can ignore air resistance. No air resistance here. Okay, so we know what that tells us. No air resistance. And we've got 5 arrows, one of 10 meters, one of 100 grams launched at a speed of 10 meters per second, one of 120 grams launched at 8 meters per second, 200 grams launched at 14 meters per second, 60 grams launched at 12 meters per second, or 40 grams launched at 6 meters per second. And the question is, which arrow reaches the greatest height? I want you to pause the video. I want you to think about it. Think about what principles at work. What is the correct response? I'll be back. Now, I really want you to pause the video, and I want you to think about this. And you know you just kept going, you scamp, and you were just waiting to hear what I was going to say. So pause the video, think about it, and then I'll let you check your work. You still haven't paused the video, you little rascal. Now go ahead and pause that video and think about this. I want you to think about the velocities and the masses are all given. What does that tell us about the subsequent trajectory of the arrow? I'll be back. Well, we know there's no air resistance, or we assume that, so everything's in free fall. And if something's in free fall, the mass doesn't matter. The acceleration, regardless of what object we're talking about, is negative 9.8 meters per second squared. So the masses are completely irrelevant. We don't have to worry about this. If I have an arrow which has a small upward velocity, it's not going to go up very far because the velocity will quickly go to 0. If I have a large velocity, it'll go up a long ways because it's going to keep going up for a longer time. The arrow that goes the highest is the one that's moving fastest, and that is the only variable you need to consider is the initial speed. Now I want to look at a problem here, and this is one having to do with a basketball player I find truly inspiring. His name was Spud Webb. He was only 5'8", which means he's about my height. He was able to jump 110 centimeters off the ground. Now check this out. Here is Spud Webb in a slam dunk competition. His hands and the ball are well above the rim. I can't even touch the bottom of the net, which is kind of crazy. So he could just jump like nobody's business. Look at how far his feet are off the ground. That's a 110 centimeter vertical leap, or putting that in meters, 1.1 meters vertical leap. Crazy. And the question is, to achieve this feat, how fast must he leave the ground? Okay? Now, we're going to solve this problem the way we do. Our first step is to strategize. How do we model the motion? Okay? And then, what are we solving for? And then we're going to sketch the velocity versus time graph for the motion. Okay, that's a lot more strategizing than we might typically do, but this is the first free fall problem we're doing, so I want to make sure we do it right. So let's take a look. Now we're going to assume that after he leaves the ground, the only force at work is gravity. It's only gravity. And that makes sense. Like, he's not moving fast enough that air resistance is going to be a big concern. So as a consequence, this is free fall. So we're going to model this as free fall. And it's free fall whether you're going up or you're coming back down. Now I want to draw a graph of velocity versus time for this motion and think about what we're solving for. So he starts by leaving the ground, and the problem is going to start at the instant that he leaves the ground. So his feet have just left the ground. 1 microsecond after his feet leave the ground, he's moving upward at a certain speed. I'm going to call that one VI. And then his speed decreases. Velocity is positive, and it decreases, and goes to 0. That's the final point of the motion. That's my VF right there, okay? And what we're looking for in this problem is we're looking for VI. What is his initial velocity? And by the way, once he reaches his highest point, as far as I'm concerned, the problem's over. We just want to know how fast he has to leave the ground to reach a certain height. We are done. That is what a graph of velocity versus time looks like. And we're looking for this initial velocity to make it to a certain height. Okay? So that's my strategize step. The next piece is we need to prepare. And for preparation, we have to draw a visual overview. And as always, we're going to look at the important points of the motion. What are the values of the different variables at that point? For each phase of the motion, if there's multiple phases, what type of motion is it? And then what sort of equations would apply? We're going to pick the equations that we will use in our solve step. So let's go ahead and do this. Now, if a basketball player is actually jumping off the ground, they're going to go into a crouch. They're going to extend their legs. At some point, they're going to be moving upward. And then at that point, they leave the ground. So I'm going to draw just a little bit of air under their feet. They've just left the ground right there. Then move upward until they reach the highest point. Now, we're only concerned with this phase of the motion, the flight through the air. We don't really care about the pushing off phase because we're not asked anything about the pushing off. We're just asked how fast must he leave the ground to reach that height. So let's not worry about the push off. We can ignore that altogether. And that simplifies our visual overview because it looks like this. The first point is the basketball player, Spud Webb, having just left the ground. So he's just left the ground. There's just a little bit of air under his feet. He's moving upward at a certain speed. So that's my initial point. Then the final point is sometime later when he reaches his highest point above the ground. And when he reaches his highest point above the ground, what is his velocity? His velocity is in fact 0. That's true at the highest point. So the initial velocity, we don't know. In fact, that's what we're solving for. The final velocity is 0. Well, we can say some other things. The initial position is just 0. The final position is 1.1 meters. Okay? And as it turns out, I'm not going to use time in this problem. And we're going to come back and take a look at why that's true. Now, between the initial point right here and the final point, the acceleration is negative, and it's negative 9.8 meters per second squared because we are modeling this as free fall. So between the initial and the final, that's what's happening. Okay? And we're going to looking for the initial velocity. We're looking for this number right here. Well, it turns out the relationship that I'm going to use looks like this. I've got a relationship for velocities, accelerations, and distances that doesn't use time. It looks like this. VF squared is equal to VI squared plus 2 times A times delta Y. And I've dropped the Y subscripts, but I've made this be delta y too because this is a vertical motion problem. I can use that relationship. And that relationship doesn't say anything about time, so I'm just not going to worry about times. The problem doesn't ask for time. I'm not given any times. Let's not worry about it. Let's save ourselves some trouble. Now, with all those variables in hand, we can move to the next step. And for the solve step, what we're looking for is this. We are looking for how fast must he leave the ground to reach this height. So we're trying to solve for, as we saw, VI. What is VI equal to? And let's go ahead and do that solution. Now, I'm going to use the basic equation that looks like this. VF squared is equal to VI squared plus 2 times A times delta y. And let's record what the different variables are. Well, the initial velocity, I don't know. That's what I'm looking for. The final velocity is 0, we said. When he reaches his highest point, he's not moving. The change in y is positive 1.1 meters because he ends up at a higher position than when he started, so the change is positive. The acceleration, though, is negative. It's negative 9.8 meters per second squared, and that means that is just because it's the acceleration of free fall. So if I put those numbers in, I get this. I get 0 is equal to vi squared plus 2 times negative 9.8 times 1.1. And I'm going to leave the units off right now just because I'm running out of room. This quantity right here is the product of two positive numbers and a negative. It's a negative number. I'm going to move that to the other side of the equation, and so I can rewrite as this way. vi squared is equal to 2 times 9.8 times 1.1. And if I solve for what vi is, I get vi is equal to 4.6 meters per second. Okay? That's what we get. Now, a problem is not complete without an assessment. Does this result make physical sense? And we can do this a couple of different ways. One is I want you to think, how long does someone stay in the air if they're doing a huge vertical leap and doing a slam dunk? I'm guessing they stay in the air for about 1 second. That's kind of what it seems to me. So if someone's speed is changing by, someone's in free fall, their speed is changing by 9.8 meters per second every second. And that means that they're, let's call 9.8 approximately 10. So if someone left the ground moving upward at 5 meters per second, that's positive 5 meters per second. At some time later, they're going to be coming back to the ground, and they're going to be coming back at the same speed as they left the ground at, and that's going to be negative 5 meters per second. The total change from going up to coming down is negative 10 meters per second. And given that the acceleration of gravity is about negative 10 meters per second, this whole arc would take about 1 second. Because it's positive 5, and to go to negative 5 is going to take it about 1 second. And that's, in fact, how much I estimated someone was in the air for, was something like 1 second. And so the result of leaving the ground at about 5 meters per second seems about right. The other way we can make sense of this is just to think about the speeds that jumping animals leave the ground at. And we're going to take a look at other animals and see what kind of numbers that we get. And we'll be able to put this in perspective. And for a human, doing a really great vertical leap, leaving the ground at like 4.6 meters per second, quite reasonable. That is quite reasonable in terms of other things that we're going to see. So net result, it does make sense. Now, after we finish talking about motion in 1 dimension, we're going to talk about motion in 2 dimensions. But the secret of talking about motion in 2 dimensions is this. We can really just break it into 2 one-dimensional motions. So here's Milo. He has left the ground. He is going after a stick in the water. His vertical motion is just free fall. He goes up and he comes back down. His horizontal motion is just uniform motion. He just keeps on moving horizontally in exactly the same velocity as when he started. And that is the next problem they're going to treat in our next sequence of slides. Now that's actually in chapter 3. So you might want to take a peek at chapter 3 before you take a look at the next set of slides. Thanks much.